let's start. So quantum computing is quite became really a hot topic these last several years. And I put this slide actually just to start from the beginning actually. And this is going to be a very short introduction in what phenomena quantum computing is using. These are very specific phenomena that are the basis of the quantum mechanics, about quantum physics, and also about the quantum technologies that we will see later what they are. So these quantum phenomena, they are not visible in the macroscopic objects, in the objects like bodies and things that we can see, but on microscopic, on very, very tiny particle level. Then this has been discovered already for quite some time, more than 100 years ago. The physicists, they are exploring, they continue researching about these phenomena, but the problem is that actually nobody knows why they are happening. Still, physicists, they have developed quite sophisticated mathematical model that can explain what is actually and how these things are happening. So these phenomena, they are superposition. So you can see here on the left-hand side, you can imagine just this sphere. And in a normal binary world where we have states of 0 and 1, which is the basis for our classical computation, we have bits, so it is 0 and 1. And we can represent them here as the poles of this sphere. Superposition is actually taking the state which is a linear combination of these two basis states that we can call them 0 and 1. So this is a linear position which can be expressed with a formula like this one. And already we are talking about quantum state, psi here, which is a linear combination of two basis states, 0 and 1. For the time being, you can just forget these brackets here, which are there to really confirm that we are talking about quantum states and not classical binary states, 0 and 1. And then there is also a condition that this is alpha squared plus beta squared is equal to 1, which is just to limit this space to this sphere. So the quantum state can be any point on this sphere and not only 1 or 0. So this is actually a phenomenon which is exploited to encode much more information in a quantum system than we can encode in a simple classical binary system. So already here you see that this point of this arrow can point anywhere on this sphere, not only on this 0 and 1. So this is the phenomenon of superposition. We can put some objects, microscopic objects, in this state, in the superposition, and then the idea is actually to exploit this, to encode the data in this superposition state. The second phenomenon, which is very, very interesting and very important, is the phenomenon of entanglement. So what is entanglement? If we have two quantum systems, we can put them in a state of a perfect correlation. We're just manipulating on one system, even though they are not physically connected anyway. The second will behave completely correlated, either positively correlated. So when we are moving the system then afterwards in one direction, then the second will move in the same direction. Or if we are moving this in one direction, this can move in the opposite direction, which is negative correlation. But in any case, they are perfectly correlated, even though they are physically not, they are disconnected. So we can put two qubits or two quantum systems in the state of entanglement. So this is how we programmatically, you will see later, how we can visualize this operation. This is a control. This is one qubit that we take as a control, and the other which is a target that we are syncing, putting in this entanglement state of two qubits. And in the end, we got this as a little formula here. So why are these formula important? Well, basically, if you want to do the quantum computing, IBM has invented a very agile way so that you don't need really to get deep immediately into quantum mechanics and into all these formulas. So you can learn a little bit the quantum theory, quantum physics, and this vector spaces, the operations, matricial operations, which is coming from linear algebra. Then you understand actually what it means using these nice visualizations, and you get coding. So you start using Qiskit to code and to test, to learn. So then this is a kind of first iteration. So when you say, well, okay, this is nice, but what can I do with this? Then you do the second iteration. So you started learning a bit more about linear algebra, about quantum mechanics. Then you go back, then you do the visualizations, then you code using Qiskit, then you see the results, then you start learning this in this iterative way. So this is very agile way actually of learning, which is different and much faster than what was a classical way of how to learn quantum computing, where you have to have very solid linear algebra, then you go to study for 1 or 2 years quantum mechanics, then afterwards you still need to study from simple to classical algorithms in the end, in a theoretical way, in the end to be able to start coding anything. So that is why I'm putting here a little bit of these formulas, but for the time being, I mean, this is just to say that behind there is a quite sophisticated model of all this. So we have interference. What is interference? When we code the information in the superposition in these quantum systems, and when we put different quantum systems in entanglement state, so what do we do then? Well, we are using this phenomenon actually when we using some operations. We are using the operations on the quantum system, overall quantum system. We are using the operations actually in order to evolve certain states towards the results that we expect to obtain with our computation. So evolving the state is repeating this operation several times. So you see, for example, if I repeat this operation on this state, 1 or 0, I will get another state. So you see that this 1 is reducing and this 0 is decreasing, is increasing. If I apply twice the same operation, you will see that this 1 going through 1 over square root of 2 is reducing further to 0. And the second 0 is actually increasing and becoming 1. So this is the phenomenon actually that we're using very consistently in quantum computing in order to evolve certain states and to get the result from our algorithm, which is the solution of our problem. So, and in the end, fourth, very, very important phenomenon is actually all this is happening in a kind of black box. If you've heard about Schrödinger's cat experiment, thought experiment, it is a cat is inside the black box. So everything is here is happening in a black box. And if we open this black box to see what is the result, actually everything collapses to these simple states 0 and 1. So this arrow here, which points to some point here on the sphere, will immediately just collapse either to 0 or to 1. And this will collapse actually maybe to 0 more times than to 1. If the arrow points closer to the point 0, if it points actually more on the northern hemisphere of this ball here, this block sphere. So we have the notion of probability. And with this notion of probability, actually, we realize that this is a stochastic process. So when we put our system in superposition, in entanglement, when we apply our operations to evolve our system to the final state, and then we measure it, we'll get one result that we don't know really if this is just based on the one experiment or only one run. If we don't know what is actually the real, what was the real position of our error in the end, it will just collapse to 0. So we'll have to repeat the whole process many times. We can repeat this process 100 times, 1,000 times. And then we will gather the probability distribution. This probability distribution actually will disclose to us what was the probability and what was exactly this error, where this error was was pointing to. So the idea is actually to do the experiment sufficient number of times in order to be able to extract this probability distribution. So you might ask, well, okay, when we run an algorithm on a classical computer, we run it just from the beginning to the end once, and we got the result. Now with the quantum computers, we have to run this experiment from the beginning until the end 1,000 times. So what is the speed up? So yeah, it's a right question, but I can reassure you that for really the problems that are classical, not our computers, classical computers are not able to resolve them, and there are many, many optimization-related problems. Even if you run the experiment on a quantum computer 1,000 times, it provides wonderful speed up over the classical computers. So this is not a hindrance at all that you have to run this experiment 1,000 times in order to extract this probability. So here on this slide, we have seen really, and I tried as much as possible to compress all these quantum mechanics that you will need for the quantum computing in just several minutes. Superposition, entanglement, interference, measurement, this is the basis of the quantum computing. So, okay, so these phenomena actually, they are used for several technologies, not only quantum computing, but for all quantum technologies. They are all exploiting the same phenomena. We are talking about quantum sensing, communications, and computing. And here you see really a lot of interest, a lot of investment by different countries. This is just continuing and accelerating. There is a lot of interest for different reasons. I mean, you will see on some of them on the slides that follow. So talking about first about quantum sensing, this is maybe the most mature part of the quantum technologies. We know about atomic clocks. They exist already since decades. Now, what researchers are trying is just to make them portable, to make them cheaper, to make them easier to use and lighter. So, and these are some of the projects that people are working on here in European Union. So this is very promising because we want to have self-driving vehicles that will themselves, that will know precisely where they are with these gyroscopes, accelerometers, using quantum sensing technologies. They can identify exactly where they are without the need of satellite navigation. Then we have gravimeters. This is very interesting for discovering what is underground, maybe some water, maybe some petrol sources, maybe there are some seismic activities, and they're very precise. So they work using different underlying technologies or modalities. But this is all quantum sensing. Or, for example, military purposes, this quantum radar, it is very, very sensitive, much more sensitive than the classical radar. Or we have microscope, which can be used in medicine to improve the level of the precision of the scanning. So you see the MRA diagnostic can be improved very important way, and other uses in a medical field. So this is quantum sensing. Quantum communications. So this is another very important field, which is also quite mature and is used for different things like super dense coding, quantum teleportation. This is actually, there are some algorithms that if you start learning about that, you will learn about them very quickly, what they are. And it is about transmitting information using much less resources than typically what you need when you're using just classical bits through the light. So this is one use case, potential use case to compress everything. Another use case is actually to create a quantum network. It means that remote entanglement, you have seen that entanglement where we put two quantum systems in perfect correlation, even though they are not connected. So the idea is, and researchers are working on that, how to put different computers actually to be able to talk with each other, or which is a very, very promising area of research, how to interconnect quantum computers. So this is so to be able directly to feed the information into the quantum computer without coding, encoding, measuring, and things like that. And another one, which is very mature and quite a lot of interest is behind this communication security. How does it work? Well, you have seen that when we measure quantum system, this arrow, it collapses immediately. So, and we don't know, we are not able really, unless we repeat this experiment 1,000 times, we are not able really to say where this arrow exactly was pointing. So, in a way, we can consider this to be like a difference between these tennis balls here and soap bubbles. You know, these tennis balls, you can capture. Imagine that there is a hand here capturing these balls and reading, and then throwing it further. So tennis players, they will maybe not realize, if it is done fast enough, they will not realize that there is any delay, that somebody is reading all these messages. But soap bubbles, that's not possible. If you capture it, it disappears. And the final recipient of these soap bubbles will see that they are no longer there. So any eventual intrusion into the communications between the sender and the recipient is immediately discovered. So that is the basis actually for the communication security, and this can be used really a lot, especially by China. So we know already since several years that they have quite significant progress in this field of quantum communications, and latest information from last year is actually that all this network was integrated terrestrial network. They have also increased the distance that these quantum states can, the photons, well, basically they're using just the photons, but where the quantum states of the photons is preserved. So initially it took only 70 kilometers. Now this can be extended to 500 kilometers. And also we know about their satellites here. Yeah, okay, so this is a field really that is progressing. There is a lot of interest in communication security based on quantum technologies. And now we are talking about quantum computers. So I wanted first to talk about this, to mention these quantum annealers. And you will hear about the D-Wave company with their 2,000 qubits or 6,000 qubits. These are very special computers that you cannot code. They are not universal quantum computers. These are optimization engines. So they are hard-coded, and you will have to use a special Ising model to encode your optimization problem. And this can work only for the optimization. It exploits the mechanism of adiabatic computer, where you are evolving slowly your state until it reaches your solution, but with a minimal energy level. So this is a slow evolution that can be used actually to implement some optimization problems like logistics and supply chain management. There is a lot of experimentation. Just the problem is that researchers, they really don't agree on the question if adiabatic quantum computers, they really provide quantum advantage comparing to the classical computers, like, for example, supercomputers. So optimization problems can be implemented on supercomputers. It can be implemented on classical normal computers, small computers. It can be implemented on a quantum annealer. And there is really no mathematical proof that quantum annealers can provide quantum advantage. It means that they are necessarily faster than classical computers. Still, it is interesting. I mean, this company, D-Wave, they have cloud services. There is quite a lot of interest among the researchers to experiment with it. What we are much more interested in is actually universal quantum computer that we can use for the optimization algorithms, but also for other computation. And this is something that So the companies they are actually working on. Here's if it is not a question for me, maybe you can go on mute, please, so that the others can hear clearly. Okay, thank you. So here on this slide, well, you can see that what is actually the architecture of quantum computing. So at the bottom here, we have a quantum processor. It is executing really the operations, putting the state in superposition in entanglement. But this has been operated by a classical computer. So your algorithms, which is a serving for you to represent the problem and to resolve it, actually it needs to be coded and calculated like a Python or like Qiskit. And then it has to be compiled, it has to be optimized on a classical computer. And
one second, Sasha. Anna, can you mute? Somebody is speaking. Yeah, thank you. Thank you. Go ahead, Sasha.
Yes. Okay. Thank you very much. So you see here that basically quite a lot of things are happening on the classical level using the classical computer. And only when those are really the instructions, the low-level instructions, they are converted into the microwave pulses, electrical pulses to control the quantum processor, then we can see that basically this quantum processor is executing those operations like how to put a system in a superposition, entanglement, and how to rotate, how to do the operations on the quantum systems. So basically, quantum computer is a combination of classical one and a quantum processor. And this is going to remain like that for the foreseeable future, next 10, 20 years. So this is the architecture. Talking about the operations, so all those mathematical formulas and actually those operations that I have explained, like we can change the state, we can they can be described, they can be visualized here in this very simple way, where we are saying that, okay, well, quantum state can be changed using different operations. This, for example, Hadamard H, this will put our system in superposition. This here, C naught, will put two systems in entanglement. And this icon here, it symbolizes measurement. So this is at the end. So this is at the result, we get the classical states, and then we have to repeat this, as I explained several times, in order to get a probability distribution. So the way how we visualize the whole circuit, the whole algorithm is actually, we can do that visually, like that. So here you see that we have two qubits, two quantum systems. And we have here, we are collecting, by measuring the state of these quantum systems, we are collecting what is their state, how it collapses, where, to 1 or to 0, and we store that in our classical bits. So you can imagine actually that this can be much larger, have tens or dozens of different qubits here, and this becomes a bit complicated when you start stacking up different base operations from this catalog of operations over quantum system. So all this we call quantum circuit. And how do we design actually quantum algorithm? As I mentioned, so we are going to exploit superposition to keep much more information in quantum states. And here you see that actually we have exponential growth of the quantum states that we can store in the quantum system. So with 50 qubits, we can represent to the power of 50 bits, or to the power of 50 states, binary states. So you can imagine that with 2,000 or 1 million qubits, how much different states we can represent. So the second step is actually to, after we use the superposition, then we are going to entangle the system so that we can parallelize the operations. The third, using the interference, we can evolve the overall state to get respective results. And in the end, we measure multiple times. We repeat this, the whole circuit multiple times to get the probability distribution. So maybe you will then say, okay, well, we can use that maybe for some weather forecast, because there is quite a lot of information there, a lot of bits data. So then we can encode in a quantum system all these states from outside. Well, big data is not a typical use case for quantum computing. It is difficult to encode. So the best problem for quantum computing is a chess type problem. You know that when you have a first move, then you need to calculate in the future what is going to happen in the next move, in the next steps. And this space for the solution, it increases. As more steps in the future you want to go, the solution space is increasing. And you want to consider as much as possible of them. So for any problem like that, optimization problem, where the solution space is increasing, quantum computer promises to be faster and to be able to get much more solutions and states actually considered without encoding that in a classical way, like we would like to encode, for example, big data, getting all those measurements from different weather sensors. So these are different hardware modalities. Companies are still exploring what to use for quantum computers. And you will see different companies like trying to work with these ion traps. These are kind of atoms where you take one electron and then it's easier to manipulate. You keep that together. And then you have laser pulses where you're moving, you are performing these operations like rotation, like superposition, like entanglement, etc. What we work on, and not only IBM, but also a couple of other companies, are superconducting qubits. So the history of superconducting circuits is long, and IBM started using superconducting circuits for quantum computers already 1990s. And by the way, the first quantum computer that was produced actually in 2002, I think, it was done by IBM. And at that time, we didn't use actually superconducting qubits, but magnetic resonance, nuclear magnetic resonance. And it turned out to be not really very promising because we were not able to put two qubits developed such way in entanglement. So this superconducting is very popular nowadays because it's fixed, it's a circuit. So here you will see, for example, this is on a chip. So this is one qubit, this is second qubit, third, and in this particular image, so here you see there are how many? 3, 6, 8, so 16. So we have 16 qubits here. These wires, basically, we use them to pass the electricity or the waves in order to control this, to put them together, to be able to entangle them. So this is one chip, and this is the size of 1 millimeter or something like that. So you can imagine that we can scale this, and we can put, for example, nowadays we have this Eagle, which has 127 qubits. The next year, IBM plans to issue Osprey, which is 433 qubits, and there is a whole roadmap that I'm going to show you. So this is how it works. It needs to be cooled to near absolute zero, and we use microwave pulses to control them. Yeah, so there is really a lot of things here to learn if you like, but what is really exciting about this is that they are static, and we can easily control them. So, yeah. There are also photonic computers. This is here just an illustration. It is using actually, probably you have heard about these photonic systems. They are using photons, but you know, photons, they are flying the speed of light, and they are difficult to control. They are difficult to put in entanglement. So that is why this technology is still developing and not really providing the basis currently for the universal computation. However, different companies, they have developed these samplers. Why sampler? Because actually it is providing the probability distribution. So it is a computer and we can code it, but the coding is limited. So currently it can be used for different use cases. Some of them, they are very similar to the machine learning use cases. For the artificial intelligence, this can be explored actually, definitely, but with some limitations. So it is not really that you are going to develop your circuit from the beginning until the end, and then you have full control over your operations. But for some of the machine learning, for example, unsupervised learning examples of this here, graphs, this is quite interesting learning platform. So what is the problem now with these computers? I mean, why are we not really currently using them for our practical use cases? So the problem is that the level of technology. So currently, these computers, they have a lot of noise. For example, here on this image, what we have is a simple operation. We flip the state. So we imagine on a quantum computer, we have state 0, and we want to change it to 1, then back to 0, 1, 0, and like that multiple times. Here we can do this 20, 40, 60, 80, 100 times. In a normal system, we expect when we flip the system from 0 to 1 and back, that always it shows 0 or 1. But with the quantum computers currently, after some time, the system starts degrading in a sense that we are losing coherence. And if we repeat several times, if we repeat this experiment multiple times, then we will see that already after 20, 30 iterations, our system completely loses the coherence. Instead of showing 1, it shows 0. And then afterwards, you see here that it just goes into the opposite direction. So this is we have identified several sources of noise here, which make the life of our coding, our programming specialist very difficult. So what we want to do is actually, and the technology is improving, but still the engineers are struggling to find, to develop a perfect fault-tolerant quantum computer, which will keep its coherence and the results stable. So there are different problems here, the interaction with the environment. We have to keep it very cool at the temperature close to absolute 0, but sometimes there are some cosmic rays coming there, small vibrations from the environment. There are the interactions between qubits. We put one qubit in one state and the other qubit in the other state, and there might be some interactions. The operations, our control equipment might be also a little bit imperfect. Measurement errors, when we are measuring, are we really measuring that it collapsed to 0, not to 1? So all this is actually producing the noise, which is a significant obstacle when we start developing all those beautiful, theoretically very useful algorithms that the researchers, physicists, they have invented already 30, 40 years ago that can be used to resolve the most difficult optimization problems in the world. So we have two things that we need to do. One is to improve the equipment, slowly, and this is happening already. So this is, for example, a chart as of 2021. Already, if we use our most modern computers, this will be different, this will be better, but still we have just incremental improvement. So improvement of the technology. The second one is a quantum error correction. So these are different models, like, for example, we want to have redundant qubits so that several physical qubits, they present one high-quality logical qubit. So that when we look at this logical qubit, we can say, well, this is very stable, and we have high-fidelity operations on this logical qubit. And underneath, there is a lot of physical qubits that some of them, they are losing coherence, but the majority they are keeping, and then we restore them to the previous state. So using this redundancy, actually, we can implement quantum error correction. So this is a still very important area of research for the physicists, for example, who want to work on quantum computing. This is maybe one of the most important areas where they are working currently. And in meanwhile, so IBM has implemented this error mitigation. So what we do is we are learning this error and noise model. And it's like when you have this headset, that you want to listen to your music in a very noisy environment. And then your headset, they are smart, so they are canceling the outside noise. So this is something that actually the same mechanism that we are using for the error mitigation, so that despite this curve here and this external source of noise, that we can still be able to deduct what the result here should be. So it helps, this error mitigation, it helps to implement deeper circuit. So here you see we are talking about circuit depth. So what is very interesting is that if you want to learn quantum computing, you can use just a local simulator. You can install Qiskit on your laptop, use your laptop, and here you can implement your quantum circuits up to 20, 25, eventually if your laptop is strong, 25 qubits. More than that, for example, if you want to have a circuit with 30 to 40 qubits, then you need to use servers. There are some companies producing some specialized devices. Then supercomputers, they can simulate up to 50 qubits or maybe 60, 55, 60. More than that, not possible. But already this is quite good, I mean, for the beginners and for even teams that are searching for how to implement some of the practical use cases and how using quantum algorithms. So what are the use cases actually? We were talking about quantum phenomena, we are talking about hardware modalities, we were talking about what are the limitations of the hardware. We were talking also about the quantum circuits, different operations. So what we can use this for? So basically, there are different things related to simulation. Here is basically simulation use cases. Value at risk, risk and scenario analysis, derivative pricing in finance. So what is the algorithm that we can use? Quantum amplitude estimation. Here you can see the names of different algorithms that have already been developed and worked out. So this already exists. And if you want to learn actually quantum computation, then definitely you will have to, you master the basics of quantum computing, then you can choose one of these quantum algorithms and work more details on that. So talking about the optimization in finance, the portfolio optimization, collateral optimization, trade settlement, combinatorial auction. So you see the different optimization scenarios that can be implemented. Either, these optimization problems, they can be either convex or combinatorial. So in case of convex, use one category of algorithms. In case of combinatorial, this is QUBO. So this is quantum unconstrained binary optimization, where you will eventually implement variational quantum eigensolvers. So this is a kind of algorithms which can work even on these noisy, NISQ noisy quantum computers. Machine learning as well in finance. This is a separate field, but it's quite interesting for fraud detection, customer scoring, forecasting, etc. And these are different machine learning, quantum machine learning algorithms that are being explored for different financial use cases through machine learning. Of course, there is a quite large area of quantum chemistry that I have not mentioned for the lack of time. And this is maybe one of the very high value added use cases category in quantum chemistry. You can imagine that nowadays chemists and scientists, in order to develop a new medicine or new material, they have to experiment, or they have to use some mathematical models which are really very imprecise. So the problem is how to deduct all those different electrons from one molecule, how they are going to interact with the electrons of another molecule if we want to simulate this synthesis of two molecules. And the space for the of the different solutions is impossible to simulate using classical computers. So eventually, when these problems with the errors, with the coherence, when they get resolved, eventually in 10, 15, 20 years, I don't know when exactly, nobody can say that, but once when we have really fault-tolerant, universal, large-scale quantum computer, you can imagine that it's going to be much easier and much faster to invent and to develop new materials. This is going to be really a great revolution, a new revolution in the material science. So here I'm focusing more on machine learning. So just wanted to show you actually that we have a support vector machines and quantum support vector machines. So this is here just to remind that support vector machines, they are used for supervised learning. And what we do with a quantum support vector machines, so we want to, this kernel that is very well known in support vector machines, we want to replace it with a quantum kernel. And of course, we can implement that for all kernels currently used in support vector machines. The problem is, do we have quantum advantage if we just implement a typical classical kernel on quantum computer? So the next step, the step beyond just implementing quantum computing for the classical kernels, is to come up with a kernel which cannot be implemented on a classical computers. So this will allow really to use quantum computers in such a way that classical support vector machines cannot be done. So here there are different ideas actually, and the researchers, they are working very hard. There is already this D-log kernel, which cannot be simulated classically. It can be implemented only on quantum computers. So the thing is, the progress there is happening. Maybe we are not yet there, but if you like to learn quantum support vector machines, also at IBM in Qiskit, we have all libraries that you can use them. And of course, if you want to go beyond, then you can join Qiskit Advocate program and learn more about what are the latest research areas in developing quantum kernels. Talking about, there is a lot of work being done on the level of quantum neural networks, different ideas, different models. So if you want to know more details, if you want to develop in this field, there is a lot of research being done currently. So quantum machine learning, how does it work? So first, as we have seen, we need to encode the data in the quantum system. So there are different ways here, using angle, amplitude, high order. Then once when we encode the data, when we pass this first step, then we are using something like in neural networks, which is a kind of network. So here we call it variational circuit. And you know that in neural networks, if you have a deep neural network and large with respect to the number of qubits, with the neurons, not qubits, but neurons, then it has more expressive power. So there is a lot of work being done. How can we create a a kind of circuit which analogously to the neural network, to one layer of the neural network, can be expressive and can help us to, in the end, to be able to learn those parameters. So some of them, for example, this one is very expressive. It has high power. And here you see that it's just, the example is on 4 qubits with different operations, rotational operations, which put these qubits in entanglement. So we want to use a circuit like this in order to be able to keep the quantum states there and to learn all those parameters like X, Z, here. All these gates are controlled by different parameters, and we want to learn them. In the end, we have measurements. When we measure, then we want to extract the label, because in machine learning, we have labels. Cat or dog, true or false, different things. So the trick is here to how to, this probability distribution, how to convert into the labels. Then, of course, we will have a cost function, then gradient descent. Gradient descent, there is also quantum gradient descents, the way how we can adapt our parameters in order to be able to minimize our cost function. In the end, we are updating the parameters and run again, encode the data, run through this variational circuit, measure again, and do this loop sufficient number of times in order to be able to minimize our cost function. So minimizing cost function, you know that we'll be able to decide which label actually is the output of our machine learning algorithm. So it's quite similar. So basically what we are trying to do is we are applying the best what we know about quantum algorithms, and the main principle of the supervised learning here is basically the same. Iterations in order to learn different parameters used for our quantum circuit. So these were the use cases in finance, machine learning. So you know that we are talking a lot about security use cases, that very soon quantum computers will be able to break the internet, the security of the internet, and so this encryption. It is true that RSA is vulnerable, but it will take, for example, for this 2048, it will require about 5,000 qubits, but these qubits need to be of high quality. And current quantum computers can't run factoring of even the number like 35. I'm not aware of any experiment that can do the factoring of this. Maybe if you use the latest computers, maybe you will be able to do it. But what I want to indicate here is that it is really very, very early to start thinking that the quantum computers can really break this RSA 2048. So it is estimated to take 30 years to get quantum computers capable of this task. You will hear about some research papers claiming that they can get this speed up in different ways, but reading them, I'm not really confident that they will be able to overcome very quickly some limitations of those approaches. So the problem is actually if you have some sensitive data that is going to be sensitive also in 30 years. So and if this has been spied, collected somewhere, so those who in 20, 30 years, I mean, pessimistic is 30 years, maybe optimistic will be shorter, but still we are talking about decades. Those who have your data, they will probably be able to use these computers in the future to decrypt it. So there are some companies that are thinking already now how to protect themselves. And in many cases, migration to new quantum safe algorithms, it takes time. So there are quite a lot of discussions and new standards being promoted by American National Standardization Organization. So there are quantum safe algorithms for this asymmetric encryption that cannot be broken by quantum computers. Symmetric schemes, they are not impacted. That's for you important to know. If you want to know more, just there is a lot of resources. Quantum random number generators. This is one very important use case for the security. I'm not going to stay here, but you can imagine that random numbers nowadays, they are pseudo-random. They are not really random. You can use some physical systems to produce random numbers, and quantum computers, they are the best sources of random numbers. You have seen it actually that one state in a superposition, it can fall to 0, it can fall to 1. If it is perfect superposition, then the probability of 0 and 1 is 0.5. So you can generate this random sequence, convert it from binary into decimal number, and then you have random number. It's very simple to do, and it is perfect random number. So this is for some use cases very important. And there are some fun use cases like this quantum chess and quantum games, where you can learn about quantum theory, quantum physics, and also about quantum computing, about different gates. There are some musicians also experimenting with new aesthetics. For me, it's I'm really not talented for music, so it's like kind of noise, but you can really you can read a lot. There are some symposiums and dedicated to quantum arts, quantum music, which is quite interesting. I mean, one can learn a lot about quantum computing as well. And just last few slides here, how does this impact you? So what is actually general recommendation? So for the general audience, professional audience, if you're in business, if you're in industry, so you can expect that in 3 to 5 years, there are going to be first practical use cases with quantum advantage. Doesn't really mean a lot, but they are, of course, going to be followed by a lot of media and hype. So they are going to be. So this technology is progressing. Then we will definitely know what is the best platform. Is it superconducting qubits, photonic, trapped ions, something else? And what is really important, I mean, there is going to be a lot of interest for that, but not a lot of access to real quantum computers. By the way, IBM is offering the membership to the organizations to be able to access larger computers. That can be interesting because you can experiment on your laptop up to 20 qubits, but if you really want to see how this works on a practical, real world quantum computer with more qubits than that, then you need really to access a quantum computer. In 10 years, there are going to be definitely new quantum algorithms, new use cases. We will see the wave of migrations to quantum safe encryption protocols. We will see also error correction mechanisms, which are the basis and foundation for the universal fault-tolerant quantum computers. And in around 20 years, I mean, this is really very difficult to estimate here, but hopefully we'll see a fault-tolerant quantum computer able to run deep circuits, and this is going to change the world. So how can you learn about quantum computing? I recommend Qiskit textbook. As I mentioned, this is completely agile way of learning. So you do practical things, you learn about quantum mechanics, but this is fun. Don't be afraid of doing that. If you want really a classical way, this is excellent book. It provides a very solid foundation about quantum information science. Then this I find really wonderful book, Quantum Programming Illustrated by Alexander Adobanovic. He really did a great job how to simplify the learning of quantum computing. This is a wonderful book. And the others, of course, Quantum Computing for Computer Scientists, or if you are interested more in machine learning, then Machine Learning with Quantum Computers by Maria Schultz. She's one of the top scientists, world scientists in quantum machine learning. So there are a lot of also the whole offering of the different online courses. Please check what is there at IBM. Every summer, there are Qiskit summer schools being organized. And this is also the way how you can learn more. Shukran, thank you. I will switch over to some practical things here that I would like to show you. So first of all, development roadmap of IBM Quantum Computers. We are here now. Eagle is there, and the end of this year. Actually, I mentioned next year, but it's scheduled for the end of this year. Is this 433 qubits, and the pipeline is already there, and the teams are working on quantum computers with more qubits and also with better wiring and high coherence platforms. So if you just go to quantum computing, ibm.com, you will see this visual composer, quantum composer, which lets you play with different operations. So here you see the available gates or operations. Here you see, this is a simulator actually, but if you build a circuit, then you can also run it against a real quantum computer. So quite a lot of quantum computers that are available for free to the general audience, so you can do that as well. But for example, if I just drag and drop here, this is going to put the state of this first qubit in superposition, and immediately here you see that when we measure how the state will collapse, we have equal probabilities that this will collapse in the state 0 and the state 1. So if I want to put 2 qubits in a okay, sorry, this is not the right gate. If I want to put 2 qubits in entanglement, then the first needs to be in superposition, and then I have this controlled gate. So here you see that I have 0, 0 and 1, 1. And this is this is not a block sphere. This is a bit more complex way how you can describe the state of multiple qubits here, 0, 0 and 1, 1. So here I can, for example, just remove this third qubit, or I can add more qubits here. So basically, this is a interesting way how you can experiment and see what is happening with the quantum states while you are developing your circuit. And here on the right-hand side, you see, for example, the assembler code that, for example, if you have longer circuits and code, then you can just exploit this in order to develop more. So next, what I have here is sorry for that. Yeah. What I wanted to show you is also how you can code with Qiskit. So Qiskit is a quantum information science kit. And you can install it if you have Python, so you just install it as a package. There are different modules within Qiskit, and basically you can use it to develop your first algorithms in a Jupyter notebook like this one here. So I'm listing here the version, and of course now if you install Qiskit, it's going to, well, there is a development community behind it, so the new versions are being produced regularly, and of course this is going to be completely different version log. So what is important is actually you can register on quantum computing platform at IBM, and you will get the API. You will have the API token. So your account here, you can save it, and then afterwards, when you load it, then you will be able to access quantum computers. Of course, if your organization is a member of IBM Quantum Network, then you will have the access to additional computers with more qubits. And not only that, you will have the access to a dedicated team. You will have the access to the information that's about the new releases of Qiskit and about new practical applied algorithms, quantum algorithms. You can also get the support if you are developing some research within your organization. So IBM Quantum Network is really for the organizations that want to work and to develop their internal teams in quantum computing. So here, this is just a account which allows the access to the freely available quantum computers at IBM. And for example, this was the list of available backends. So you see here the names. So it doesn't mean that the computer is really in Spain, in Valencia, or in Melbourne. They are in the US, but simply we just distinguish them with the names of different cities. If you want to see their features, then you can just run this tools monitor backend overview function, and you will see, for example, how many pending jobs are there. This is important because sometimes this number of jobs can be quite large. So if you want to run against a real backend, then first you will check this. For example, here there is pending job 643. So probably you will choose a computer with less pending jobs to be executed. This is one computer 16. It has actually 15 qubits. So the others, you see that they are 5 qubits. So if you want to experiment with 15 qubits for free, you can also do it. And here you can get for one particular computer much more information about technical features. What is important for you to know is this architecture. This is topology. What this here means is qubit 0 is connected to qubit 1 directly, and also to qubit 14. Yeah, so here you can see, for example, 1 is connected directly to qubit 2. 2 is connected to qubit 3. So this describes to you the topology. Why is this important? Well, if you want to implement entanglement, so you want to avoid actually that in your circuit you say, well, 1 is going to be entangled with qubits 2, 3, 5, 6, 7, because then the system, the transpiler, this is the optimizer, will have to go through this topology map and to look for how to convert your entanglement schema into what is physically really available, where the links physically exist. So if you already know where the physical links may be during the design of your circuit, you will then just consider these physical connections and then design your circuit in order to reflect the best what hardware you have. And of course, if you want to have a portable code that can be ported to another computer, then you will rely on this optimizer, which can do a really good job in optimizing your circuit so that it can reduce and compress the time necessary for the execution. So here you see, for example, some technical features like what is the coherence time, what is the error level here of different gates, and basically the way how you can code in Python and Qiskit is first you are going to create a circuit, so this here, and then you can apply your gates with these abbreviations like Hadamard. So this is going to put the first qubit in superposition, and here I put 0, so this is on Q0, and this is a controlled X gate or controlled flip gate, which taken together is going to put these 2 qubits in entanglement. I can also add these measurement commands, and then this is going actually to provide the result. So as we have seen, the whole system is going to collapse into the classical state. And in the end, we can run the whole circuit 1,000 times in order to collect the probability distribution. So here we were plotting the results, and we see that basically based on this entangled system, they are collapsing in these two states, combined states. So this is the probability distribution of that quantum system. So you will see here 509, 491. Why is this not 0.5 and 0.5? Well, there is also certain randomness also integrated in the simulator, so that it gives you the notion of approximately what you would receive when you run this on a real quantum computer. What is the advantage actually? Where do we see this? How can we see that quantum computers can do something that classical computers cannot? This is a very simple example where we can see that. So this is bit addition. So you know that 0 plus 0 is 0, 0, 0 plus 1, 0, 1, 1 plus 0 is 0, 1 again, and 1 plus 1 is 1, 0. Well, here we have 4 operations, and I went through them through each operation once. So in total, I went through 4 operations. Well, classical computer will also have to run through this 4 times. Quantum computer can do the whole operation once. And that is where we can see the advantage. How do we do that? We implement a circuit, which is made of 3 qubits. So why 3? We are talking about 2 numbers here, 0 and 1. So that is true, but we need a 3rd qubit in order to represent our carry bit. So if you want to go further, if you have more numbers, so the number of qubits that you will need is 2 to the power of n, where this represents actually the number of bits. So we need only n. We need the exponent of the qubits. So if you want to have a billion of numbers, so you will not need billion qubits. You will need only this exponent n, where 2 to the power of n is your number of the length of your number. So n plus 1 for the carry bit. So then we are applying superposition. We have this double control X gate. Only if the first qubit is in 1 and the second qubit is in 1, then it is going to flip the state of the 3rd qubit. Then we have just a simple control X gate, and we are measuring. So you hear this barrier commands, which just indicate that we want to visually to separate these operations. It's nicer. And then when we run this 1,000 times, we get a probability distribution that is giving us the results. This is 1, this is 1, 0, and this is 1, 0, 0. This is the result of 0 plus 0. This here is the result of 0 plus 1 and 1 plus 0. And this here is the result of 1 plus 1. So we got this, we went through this circuit, and we calculated 4 operations simultaneously. And this is something that basically demonstrates that parallel execution of multiple operations on quantum computers. So the rest is actually just a kind of visualizations and how you can use different commands in order to learn how to visualize. You have seen that state can be in a basis state, so this really represents just like a classical state, but this arrow can point anywhere, and we can, of course, we can rotate it and measure it. In order to visualize several qubits, you can still use this block sphere, but if the qubits are in entanglement, then this is not enough. So you will need to use different ways of visualizing it. So all this is very useful when you start learning about it. Once when you get the notion and the feeling for how different operations they translate into the change of the states and where this can go. So you will not need this simple visualization anymore. So let me show you quantum machine learning. So when we are talking about quantum machine learning, then there are two actually things how quantum computing and machine learning, they can be integrated. So we can use machine learning for quantum computing. I mentioned this noise cancellation. So this is typically where we can use machine learning in order to predict where the noise is in order to improve our quantum computers. But what we are mostly interested in is quantum enhanced machine learning. So what machine learning techniques can be improved by using quantum computers. So there is a lot of work that has been done there. So linear regression, ridge regression, perceptrons, support vector machines that we mentioned, etc., etc. So it's an ongoing research. And one of the most popular nowadays in this era of noisy computers, noisy quantum computers, is this variational quantum algorithm. I have talked about this already, but just to repeat once again, so we are going to encode the data, then use the variational circuit, which kind of represents a neural network, run it, measure it, then use this data, this probability distribution, to pass through a cost function and classical optimizer. It means that parameters that we used actually here are going to be tweaked, like in a classical neural network training. And then we are going to encode again and use these new tweaked parameters in our variational quantum algorithm, to pass again. And we are going to repeat this loop multiple times until the convergence. So here is actually the way how we can demonstrate. For example, we can develop a simple quantum classifier with 4 qubits. And this is the circuit which is going to implement this part here. This is the circuit here. And what is happening here? How do we calculate the gradient? So once when we measure that, these are the parameters, of course. When we measure that, then we are going to apply, this is a quadratic loss function, and we can calculate this delta as a label minus prediction that we get. So, and we use this simple gradient descent parameter shift rule in order to calculate this gradient of the parameters with respect to the quantum circuit in order to update our parameters. So we have forward and backward pass functions here, which are just helping us to move through the quantum circuit and also to calculate the gradient descent. And then we are running here the training, the loss calculation, and in the end, we can see that how it evolves. This is just a simple classifier using the quantum computing in order to encode these parameters and the measurement of the quantum circuit. So in the end, we see that how it converges. So this is the loss, and this is the prediction, which grows until 1 here, because this is what we want to predict, starting from 0 to 5, which is random prediction, to 1. So this is just a small example of how to implement this very simple variational classifier. And this is an example of how to implement support vector machine using, so if you have noticed here in this variational classifier, I'm using just a very simple Qiskit and NumPy. I'm not using anything else here. This is low-level coding, which demonstrates how to use quantum algorithm here. With it's very simple. We are just using different simple commands that we have seen already. I mean, that I have showed to you earlier. But for example, for support vector machines, there is already a library developed by IBM for the quantum support vector machine. So if you remember support vector machines, it wants to maximize this margin here in order to find a classifier between two groups. And here we are going to import quantum support vector machine from Aqua in algorithms. Aqua is a part of Qiskit which contains a lot of applied quantum algorithms in optimization, machine learning, quantum chemistry, etc. So one of them is quantum support vector machines. And here we have different kernels or feature maps. So this is one, just a simple example how, for example, we can visualize this training data. These are the training data here. This belongs to class A, and these are the training data that belong to class B. And normally, here we have test data. Normally, you see that this should belong to class A. This here definitely to class B. And this is a little bit more to the right. So if we have the line separating these two classes, going just to pass a little bit to the left of this dot here. So it should belong to class B. So implementing support vector machines, quantum support vector machines here, we can use the data. Here you see we are passing training data set and also testing data set because we want to test and to see how accurate it is. And we are going to run this quantum support vector machines in order to provide the result and to print what are the predictions. So here running, you see that here we are just printing the result, and the result is obtained through running of quantum support vector machines. And this here quantum instance is basically coming from this quantum support vector machines engine, which is fed with the training data. As the result, we get AABB, which is according to our expectation that this dot here should be classified as B. So this is one-dimensional data set, and you can also go with more data, with more complex examples. Like here, we have two-dimensional data set. This is the training data, and here this is the test data set. So we want to be able to classify, to identify if these dots here, they belong to class A or to class B. So this is the test data set, and I'm visualizing here to show you how this should look like. So this is the data labeled test data set. So again, running with a different feature map. This here is with more qubits with the entanglement. So this is a bit more serious because the data is two-dimensional. We are running the same way, and then we have a comparison of our predictions and what the ground truth is. How this, what are the labels of these data points here in a test data set, and we see that our algorithm also works efficiently and effectively. So this is something that you can also play with, quantum support vector machines, the part of our Qiskit module. And with that, I think that I have closed this part of my presentation. Thank you very much.